So, as always, guys, I always recommend when you guys are either studying for your mastery test or starting a new lesson for any of your classes, not just math, always read your objective. This will help you kind of realize what you're supposed to be learning. So, in this case, we want to develop definitions for rotation, reflections, and translation. So, our goal for today is figuring out what these three words mean in terms of angles, circles, perpendicular lines, parallel lines, and line segments. So we have to understand what these three words mean when it comes to one, two, three, four, five, these four objects. So always take a look at this so you can understand what the goals of the lessons are. So in the introduction, they're talking about a software programmer who's creating a game for phones and tablets, and his goal is to kind of like move these objects around, but they don't change shape, so they don't get bigger, smaller, or anything. He just needs to program it where these objects can take shape. So I think that was one of the things we covered at the beginning with careers. Game development does require a lot of geometry because we're talking about how to move things. So, for example, how these little monsters are going to be moving, how the little spaceship's going to move, how the bullets are going to move. So, all of that requires geometry in the sense of transformation. And those transformations are going to involve what I said before, the translation, reflection, rotation, all of that. Because it's not in this game because this looks like it's what is this, Space Invaders. But if you had asteroids, the little ship rotates and stuff. So when it comes to transformations, we're specifically talking about rigid motion transformations. So rigid transformations, that's when the distance of any pair of points in the image is equidistant between corresponding image. So basically, all of that is saying that it doesn't change size. Like it doesn't get bigger, it doesn't get smaller. The size of it doesn't change. Angle between the pair of segments doesn't change. So you can kind of keep the shape, or not necessarily the shape, but you can keep the size but change the angles. So for example, let me pull out my pen. So for example, you can have like the distance the distance between here be like 4 and here be 3. But if you do something like this can still be 4 and 3, but guess what? They're not the same anymore because you changed this angle. So the idea of rigid transformation is this idea of the distance staying the same and the angle staying the same. That keeps the shape the same. So we're going to talk about rotations first. So this is like I said with the little asteroids, or in this case, what they're doing is satellites. Satellites are literally rotating around this, but this satellite itself doesn't change shape. It's literally just going around something. And that something is going to be known as our, let me use a different color, is going to be known as our point of rotation. So in this case, the point of rotation would be the center of the world, because even though it's rotating around this big circle right here, it has to have a pinpoint center, and that's going to be the center of this. So moving on from here. So when we're moving on to the GeoGebra, as always, Admentum always provides a little link to our GeoGebra. So as long as you have an account, it's kind of easy to fix. Oh, there we go. It was taking a while to load. You can just click the link here and we can go straight into rotations. So here we see that here's our triangle, here's our ABC. And if we rotate here, this thing right here is going to move this ABC into what's known as an image. I don't think I ever went over the definition of an image. So a pre-image is where we start off. An image is like where it changes into. So this A prime, B prime, C prime is going to be called our image. This original A, B, C is just known as our pre-image. So what we're doing here is we're rotating a pre-image into other spots. So if I look here, this DEF is the image after we rotate it 45 degrees. So on here, we're literally just going to type in 45 degrees. Now, if you want to get fancy, you can always use the equation editor to type in 45 and type in the little degree symbol if you want to be all fancy. If not, like it's fine. You can just leave it as 45. I don't mind. Sorry. Rotation for DEF, 45. This one is obviously 0. We haven't moved it at all. So if we go back to 0, it's not rotated. 45 would be right here. The next one at, what is that? HIG would be at 115. So when we go here, this GHI, 115. When we go over here, we're going to rotate it. I get 210. So which triangle is that? JKL is 210. Go here, 210. So that one's pretty simple. Now it's going to ask us create a circle that passes through point A. Two more circles passing through ABC. Use the slider again. So what they want us to do is point A, point P, sorry, point P through A. So what they want us to do here, we're going to grab our circle through a point. So we click our center, and we want our point to be A. So one thing that we notice is look at how all these points fit within the circle. So that means that this is going to be our center of rotation. It's going to rotate about this circle. And then it wants us to make another circle through point B. So same thing here. All the corresponding angles, all the angles that where we would rotate to are in the circle. So if we go to point C, same thing, all the corresponding things. So this is what we're talking about when it comes to circles and rotation. So all the corresponding points would be within the circle because it's going to rotate. It's going to go around this circle. So you can see that all of the points, all 3 points are staying within those circles. So that's why one of the objectives was knowing how it relates to circles. You can see it's all going in those circles. Now what I'm going to do to show that I've done this is I'm going to click share. Since I already have an account, it's already shared with me. So I'm just going to type in my name, type in Victor, save it. And what this does is this allows me to kind of like show that, hey, I did make these circles, and I'm going to write my observation. And I'm going to write down that all the corresponding vertices fit within the circle. So this is kind of my proof saying that I did do it. Oops, I didn't copy it down. A meet link. Let's click copy. There we go. I like read it. I'm like, why does it say meet? So here's the GeoGebra link for my saved thing. So if anyone goes, they can see any one of my images. So having having an account gives you the benefit of having all of these images. All of these, by the way, are probably, well, like with the exception of like everything from here downward, are activities that we will do in class eventually. So if you ever need help with an activity, let me know. I've probably already done it before at this point. Corresponding vertices would fit within the circle. And that was what our observation was. They're always within that circle. And the word corresponding means what it would be in the other end. So I'm going to go back here. So for example, point A corresponds with D, point D corresponds with this, A also corresponds with G, so on and so forth. So now it wants us to do the angle measurements when it's corresponding. So what I'm going to do here is I'm going to click the undo button because I want all these circles gone for right now. Also, what you can do, guys, if you don't want to delete your circles, you can always hide your circles by going over here. Circles, ovals, all of that are known as conics. You can just click this on the side. Let me make this a little bigger. And it hides your circles, but they're still there if you ever want to show it again. So for right now, I guess I'll hide them. And it wants us to do our measurements. So here's the tricky part. We always want to go counterclockwise. So in this case, if I want angle A, I'm going to go CAB. So I'll go CAB. If I want angle B, counterclockwise is this way. So I want to go from A to C. So I'm going to go A, B, C. And if I want angle C, I want to go B, C, A. And for some reason that didn't work. B, C, A. I don't think I'm clicking the dot. B, C. There we go. A. Okay. Sometimes Geogebra just likes giving us a hard time. So I've noticed that you do have to kind of play with it a little bit. I've had other teachers tell me too. I was like, hey, I've asked teachers, I'm like, how do you, get this to work? And it's like, sometimes you just have to try more than one. So what's nice of what they're letting us do is if we read this, it wants us to compare it to A prime, B prime, C prime. So they're saying instead of taking the measurements of all of these angles, these three angles, then these three, and then this three, it's like, hey, just measure these angles. So I'm going to go ahead and do that right now. I'm just going to go ahead and measure the angles. So I'm going to go C, A, B, and I actually got really lucky on that one because I forgot to focus on counterclockwise. Counterclockwise would be going this way. So I want to go to C. Does everyone kind of understand counterclockwise? Now's a good time to let me know if you don't understand how to do it. Also, you can just do trial and error. A lot of times I just hit the undo button and keep trying. But does everyone kind of understand how to do counterclockwise when it comes to measuring these angles? Yes, no, maybe? You can write on the chat if you guys don't want to turn your mic on. Everybody understand it? Can you guys hear me okay? Cool. All right. All right, cool, guys. I just want to make sure you guys are able to hear me. So what I'm doing here is you can see that these angles match. So to make sure that they always match with all of these things, what we're going to do is we're just going to move them here. Oh, look, they match. They overlap and they still match. As soon as I can get it right at that 115. There we go. And then if I go over here to 210, they also still match. So what I'm going to do here essentially is I'm just copying it because A corresponds with D and B corresponds with E and C corresponds with F, as long as it's in the same order. So for example, if I had something like angle EFD, well, A doesn't correspond with E, so this would be a completely different angle. So all of these kind of correspond with each other, so I'm just going to fill it out. So the first thing for angle A is 45 degrees. So here, 45. That means all of these should be 45. That's not even like a debate. You saw that they overlapped. It's fine. Now I'm going to look for angle C because it's ACB, which means we're talking about angle C, ACB, which is 26.57, 26.57. And if you're lazy like I am, I just go Control C. If you're on a Mac, Command C, then Command V or Control V, Control V, Control V. Guess what? You just finished that part. Now this one wants angle A. So if I look at angle, oops, why didn't anybody tell me I was doing the wrong angle? This is supposed to be angle A. I'm sorry, guys. But now you guys can see that little trick I'm doing to make it faster. And angle A, angle, this was angle B. So angle B is in the middle. So it wants this angle, this 108.43. 108.53. And what's cool about this is I can show you guys another trick. Control C. If you highlight all of this and do Control V, it replaces it for you. So if you guys never knew that before, that's a good way to kind of like get rid of your mistakes. Just highlight and do it there. So now it wants you to do the measurements of ABC, compare when they collide with the other images. What do you say about the preservation of angle measurements? So that's all it's saying. All you would answer for that would be if you rotate an object, or just to use geometry terms. You can use the word object, that's fine. When you guys, if you guys ever get into computer programming, they use the term object when referring to something. In geometry, they use the word pre-image. When you rotate a pre-image the angles in the image remain same. So that's just saying that whatever you rotate, in this case it's our little triangle, all of our angles are going to stay the same. That's all this is saying. Now we're going to measure the lengths. So what do you guys think is going to happen to the lengths? Like, if the angle stayed the same, the length should stay the same too. All we're doing here is just proving that fact. So what I'm going to do here is I'm going to save this again. I'm going to click share. And now it's saved that I'm doing the angles. So I can always copy it. And if you notice, because I just changed it from something I already did, it should be the exact, oh, it actually changed. That's useful. Okay, cool. So I didn't know that, guys. That's useful to know. So if you click share again, it's going to change your image so the teachers can see that one of them has angles and the other one, if I go to this one, this is going to be the one with circles. Go here and I paste it. This is the one with my circles. But if I go to this one, without having to save anything, I paste this. This is the one with my angles. So that's a good way to kind of prove to your teacher that you're doing work. Oftentimes, like, I'm checking these to make sure people are doing work. And a good way to kind of just have your teacher not suspect you of anything, just put these links in there. It's not going to hurt you to put these links in there. And all you have to do, again, like I said, is you just click this little share button and copy that link. All right, so now I'm going to hide. I don't want to see these angles here. Oops. So because I don't want to see these angles, I'm going to hide all of them. They're still there if anyone ever wants to turn them back on, but I don't want to see them right now because I want to focus on distance. So distance, I like doing distance a lot more than angles because you just click on your 2 points and you're good. Whereas when you're doing angles, you have to focus on the rotation. And if you guys find it a little crowded here, what you can do is you can click your little arrow and it lets you move these to a better spot. I'm going to do this distance again. So I'm going to click distance or length. Boom. Here to there, here to here. Use my little arrow to move these out of the way. And what I can do now is Did I lose my rotation thingy? I think I lost my rotation thingy somewhere. Where's my slider? Number segment input. Right. I don't know where my slider went. They must have not programmed it well. But the main idea, guys, is we know that all of these sides are the same. So you can do it this way. Just copy your link so you can click share. So we're going to share it. It's going to create a brand new link, this time with the distances on there. And you can paste it so whichever teacher is looking at it can see that you've done it. So for length, let's find the length of AB. AB is 1.41. Cool. Next one I'm assuming is BC. BC is 224. And if I ever don't want to look at this, guys, you can actually go up here to distance and it'll actually tell you your distances. AB, AC, BC. Because I use that distance thing, there's a little thing here on the side that kind of tells you all the information. So you don't have to look for it. Sometimes when you've already done it and you want an exact distance, you can just look right here. So AC is 3. So if I go back here, my AC is 3. I still need my BC. I forgot to write that down. Go here, 224. 2.24. And again, because we already know the fact that these distances are the same, I'm just going to copy and paste and do here. You can even, so if you go here, it doesn't look like you can copy. So that's why you have to use the Control C. Same thing here. Control C, Control V, Control V, Control V. I mean, that one was a 3, so it might have been faster to type it out. What do we know about the measurement? So we're just going to say length of a pre-image is the same when rotated. That's all we're doing. Self-evaluation. So if you found any of this hard, guys, that's the spot to kind of say what you're doing. Remember, you're not going to get graded down if you put yourself a 1. Like, if you put yourself a 1, it's like, I had no idea how to do any of this until I saw Mr. Victor kind of do it. That's fine. That lets everybody know, that lets your teacher know that, hey, the cohorts are working. If it's like 5, like a 4, like, oh, I understood it, but, seeing it demonstrated made it better. That's great. If you're like, well, this was really easy for me, so I didn't need to see anyone do it, that's fine as well. Just let us know how you're doing honestly. So here's the idea that we're keeping the distances the same. The distances in between all this is the same. The distances here. So we kind of prove this because it stayed within the circle. So for example, A prime and A are the same distance. So remember, a circle is a center with equal points all the way around. So if I grab my thing, this idea that they have the same radius. So from here to here, you can imagine it as like a circle. Just imagine I did it better. And this right here is my radius of that circle. So that's how we proved it, by putting those circles in there. So here it's saying, hey, we take this thing right here and we're going to rotate it. What's going to happen to the angle? Well, we know it stays the same, so we're literally just going to type in 31. Rotation doesn't change the shape. That's it. So now we're going to talk about reflection. So reflection in video games are kind of how you make water look really cool. You see that it's reflecting on there, so you can tell it's kind of a reflective, or in this case, they also say metallic surfaces, polished surfaces, mirrors. So if you're ever programming a video game, what makes it realistic is having those reflective surfaces. Surfaces. I'm sorry. So let's get into this activity. So here, I'm going to click my reflections and close this other stuff. So here, this is my line of reflection. So if I move this H, it kind of does this weird thing here where because they're not letting me move, oh, they do let me do that. You can move the entire line, or you can rotate your point G and it rotates your line. So I did not know this. I was helping students with this before and I didn't know you could just move the line like this. So let me just reset this back to how it was before. Okay, so here we go. Back to how we started. All right, so change the reflection line. Can you make the endpoint eventually individually or move the entire line? As you move the line of reflection, what do you observe about the relationship of this angle? So if I move this closer to this image, notice how the points get closer. If I move this away, this gets further away. So I would write something like that. And then I can actually pass through it and it just looks weird. It's reflecting this way. So the distance from one point to the corresponding point is always the same. So that's kind of what they're going to be leading up to, but you can say as the line, let me capitalize this because grammar is important. As the line moves closer to the pre-image, the image moves closer to the line. That's what I would observe from moving this line. All right, so be sure the polygon is not touching the line segment connecting that intersects with a GE. So it's not touching that. Notice that. Draw a line segment connecting. Okay, we want to connect this one and the So what we're going to do here to connect it, the easiest way to do that is, let me move this away first. I'm going to connect this G to the A. Here, and then I can kind of rotate this around. So what's happening here is if I make it connect, they're touching each other. So record the measurement of the angles. Intersect here, reflection, GH, mark the point of intersection as AG that. Measure and record the angles of intersection. What do you notice happens with the line of reflection? So here what we're going to do is we're just going to compare the angles like we did before. So let me see if there's already a tool. They haven't measured the angles yet. But one cool thing is we can see that they did already measure the side lengths. So the side lengths are already here. We can always use that later. Now I'm just going to move this away for now. So let's measure the angles. But the main idea is going to be that these are all the same. So that's a 90-degree angle. Oops, I did that one. No. Oh my God. Oh, I didn't have it on angle measurement. Sorry, guys. So once you kind of get a pattern down, it's easy to kind of measure all of them. If you kind of get that pattern down. Sometimes GeoGebra does not agree with you guys. So that's another thing I want you guys to realize is GeoGebra is very finicky. So sometimes you do kind of have to, unfortunately, mess with it a bit to kind of make sure that you're getting everything right. So nothing's perfect. So just be aware of that. All right, cool. So what we notice here is that all the angles remain the same no matter how we're doing this. So I believe that's what this was asking. Measure and record the angles of that and that. Oh, I see what did it. We're probably going to do that later. But what they wanted us to do, I'm sorry, guys. Well, we have this down, so we can always do that later. Is they wanted me to measure this angle. So they wanted me to go like this and measure the angle. I'm going to let you guys know right now, it's a 90-degree angle. I really hate when they make you do these activities, but they want you to basically do this. And then what they want you to do is they want you to you put a little point here, and then you measure it, and that point's going to be 90 degrees. They really need to work on their wording for it. Oh my gosh. I'm sorry, guys. There we go. And I've done this before. It's very finicky. So it's a 90-degree angle. And one of the things you'll notice is if I move this around, it's always going to be 90 degrees. So what this is just saying is the distance from here to here is always going to be 90 degrees. So if you make a line from a point to a corresponding point, the angle it for the corresponding point it is perpendicular to the line of reflection. So in case you guys were wondering when that perpendicular comes into play, that's right here with reflection. So it's going to make a perpendicular line. This is just saying that if you want to measure the line from here to the line of reflection, it has to be a 90-degree angle. So from here to here has to be 90 degrees for us to measure it. Now, what it wants us to do here is it wants us to measure the distance. So what we're going to do is we're going to do it several times. From here to here, point of reflection, point of that. So A to point of intersection, A to here. So they want us to measure this a few times. So what I'm going to do is I'm going to do distance here to here, here to here, and the last one they wanted us to do was here to here. So basically they want us to do the whole thing from here only to here, from here only to there. And what we'll notice is it's always half. So I'm going to measure this one. I'm going to say all the way through is 8.8. This is 4.25. This is 4.25. Now I'm going to change this line. I'm going to move it closer. If I can actually do this. There we go. Move it closer. Let me see if I can get a perfect number in here. There we go. So 7, 3.5, 7, 3.5, 3.5. So since I know it's always half, I'm just going to do 8, 4, and 4. And to prove this, I can always do my share, save. This lets the teacher know that I actually did it. Oops, control. Did I not copy it? I did not copy it. There we go. What do we know about the corresponding thing? So we're just going to say that all of them are always the same distance. So the distance from a point on the pre-image to the line of reflection is equal to, or we can say congruent. I'll say congruent. It's congruent to the distance of the corresponding point on the image. And honestly, guys, you don't even have to say on the image. You could just say the corresponding point. I'm just being really specific here. So it's congruent to the corresponding point on the image. Again, you don't need to say this. Corresponding point on the image and the point and the line of reflection. I almost said point because I thought we were still on rotation. So all this is saying, guys, is saying that here, so the line of reflection is equal to the line of reflection to the original image. That's all it's saying. We can ignore this one because all that's doing is cutting it in half. Because these two are equal, of course it's going to be cut in half. They're equal. That's how you cut it in half. So now this is just going to say, this is what I kind of jumped the gun on before, guys. I did the angle measurements. So I'm just going to copy this down since I already have it. So to make it easier on myself, I'm going to go to, oh, this doesn't make it easier because I forget to use Greek letters. So angle A is 90, angle B is also 90. So angle A is 90, angle B is 90, which means this is 90, which means this is 90. Angle C is 45, and angle D is 135. So angle C is 45, and angle C is 135. And then we can copy it over here. I didn't copy and paste because we didn't have to do as many this time. So it's easier to type it out. Is everyone understanding this? I'm sorry, I haven't checked in with you guys in a bit. Everybody good? I know it's a little boring watching someone else do it, but is it making sense? Okay, cool. Um, like I said, right now I know it's kind of boring, guys, but these do get a lot harder. That's why I did like I don't skip these. I want you guys to kind of understand it all the way through because they get harder. So maybe I might do something that you guys didn't realize you can do, but this makes it a little easier. So now I want the distance. So I'm not even gonna measure it just because I know. Oh wait, yep, you're gonna want to measure them. I was gonna say, I was like, oh, I know that these are this, but if you don't know what this little a means, that definition could be weird. So go to distance, distance or length, click, 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 click. There's too much stuff. I'm gonna start hiding things. So for example, I'm going to hide all my angles. I'm going to hide these lines, not the line segments, the lines. I want the lines to be hidden right now. Where's lines? Where's segments? I don't want my segments gone. Points. Ah, here we go. So I got rid of that line. So now I can see this. So AB 1.41, BC 2.83, 2 and 1.41. 2, 1.41. And we're just going to copy all of this again. Copy, paste. This I know is the same apparently. I can just type in a 2. And that's all you have to do. And what's the observation that we do here? All the angles and the line segments remain congruent when we reflect. And then your self evaluation again. I would probably say the hardest part for me, like when evaluating this, was understanding what it meant. Like I know the concepts that they're trying to prove. And for example, this one was weird to me. This idea of like measuring A to AGE. They should have called this A prime. But unfortunately, GeoGebra, when you reflect, it identifies this point based on the line that you're reflecting it from. So that makes it a little weird. So that's question 3 would be probably my struggle. Here we can see that it's just saying that this is equal to this. It makes a 90-degree angle. So that's basically what we were supposed to take away from the lesson that we did. Moving on to here, what is the relationship between the line? So it's talking about that we're reflecting, we have this line, and then we have this shape and this shape. And it's saying, what's the relationship between this line and this? And we're going to say that it makes a perpendicular angle. Obviously, this isn't an exact reflection because this should be equal, but it's not equal to this. So forgive my drawing. But what can we know about this? Well, we know that they're perpendicular. That's what we were supposed to take away from this, is that, oops, coincide. What do you mean it's not perpendicular? The distance is infinitely many. Okay, so it is perpendicular. It's just that's not what they were asking for. What is the relationship between this and line L? It's perpendicular. Oh, it's not a. Yeah, it should be a perpendicular bisector. I don't know what's wrong with this one, guys. This to me doesn't make any sense because it does bisect it perpendicularly, unless it's saying it the other way. The line L bisects. Oh, I did it backwards. That's what it's saying. This line. Okay. I did it too fast, guys. Make sure you read everything. That was me reading it too fast. It's saying that this line is going to bisect this line. So what I put first, I said that this line right here, this blue line bisects this line. And it's saying, when I picked it, it said that can't happen because this line goes on forever and goes on forever. So you can't bisect something that goes on forever. That's why I got that one wrong. It's literally just because I had these backwards. So translations in video games, that just means when you're moving stuff around. They're showing a chessboard because whenever we do play chess, for example, if I'm moving my knight, it moves up 2 over 1. So that's a direct translation. Like this horse would move over here. Pawn would always move forward 1. So they all have different versions of translation. So we're going to learn about translation in this next activity. So let me delete this. So they want us to figure out the slope and everything from translating. So first it's like begin translating this, create a line segment, 5 units from A, B, C, D. And we're going to do that. So let's look at the translation activity to see what it's talking about. So they want us to translate this. So when we translate this, move it certain way, find the slope, blah, blah, blah. So when we're translating, they want us to use this translate feature right here. Where is it? I thought it was here. Ah, there's a translate feature here somewhere. Oh, here we are. Anytime we're talking about rotation, reflections, dilations, and stuff, guys, it's going to be this one with the 2 points. Basically, I believe it's the blue is your pre-image, the red is your image. So here, what we're going to do is we're going to click translate by vector. This one's going to be really hard if you don't have a mouse, unfortunately. But what I recommend doing is clicking it on your touchpad and then dragging it with another finger. So that's going to create this image here. So what we're going to do here is they want us to find the line segment. So line segment of what? Connect the points created, form the polygon, congruent. Blah, blah, blah. When you're done, translate the polygon 5 units up. So they want us to move it 5 units up, which is really hard. I don't know how they want us to exactly move that, but if easiest way to do it is, since this is at -5, what we can do is just move this over to 0, because that's us moving it 5 units. All right. So now measure the slopes and everything. So what I'm going to do here, if I want to measure the distance, literally I'm just going to grab this to measure the distance from here to here. And then I'm going to measure the distance from here to here. Notice I don't even have to do a line, guys. It literally just works out perfectly. So as you can tell, I didn't move it exactly 5 units, but that's okay. We're going to assume that we did, and we're going to call it 5. They said make a line segment. I'm not going to make a line segment because you can just measure the distance. If you want to make a line segment, that's fine. That's a good visual way of showing it. Go here, make your line segment. It's going to be the same answer regardless. Then it wants you to calculate the slope. Well, I moved it 5 units to the right. So if I measure the slope, it should be 0. Let's see how accurate I moved it 5 units to the right. It's a little hard to do again, so my slope might not be exactly 0. So I'm going to measure this line segment right here. Oops. Let me undo that. I forget. They actually make this really easy, guys. You literally just click on the line and it measures it. Oh, look, I did it pretty good. I did it right at 0. So again, you can make your line segments, but I can tell you right now, these are all going to be 0. You can measure them if you want, but I can guarantee you it's all going to be 0 because we didn't do anything. So how do we know about the line segment? So we're going to say the distance between corresponding, and remember, corresponding just means where it moves to. Corresponding points is always the same, as well as their slope. And honestly, guys, just write that better. I'm just kind of rushing a little bit. But basically, the distance is going to be the same, and the slope between the corresponding points is also the same. So you guys might want to write that a little better. But as long as I get this idea that the slope and the distances are the same, that's fine. Now what they want us to do is they want us to move 8 units down. So when I'm looking at this, I want to move 8 units down. So I'm going to go from -1, or from 1 all the way to -8. So I'm going to use my translate by vector, and I'm going to stop it. I'm going to move this down 8 units. So I'm going to grab this, translate by vector, and I'm going to move this down to -7, right there. All right, and now they want us to measure from where to where. Where do they want us to measure? Measure the line segment, construct path. So they want us to do the same thing. So again, guys, because we know that this is going to be the same, we can just make that. We're going to make our slope, calculate the slope of this line segment. It's a 1. They moved it equidistant this way. And, oh, not 1, sorry. They're doing it rise over run. They're saying our run is 1 and our rise is negative that. So if we wanted to do this, what we would end up saying is, what's our slope? negative 1.6. All the slopes are always going to be the same. If you want to do it, more power to you. That's how we're supposed to do it. If we're in a hurry and we already kind of defined that, like, I'm not going to put it against you if you don't do it, but you can. Let me just prove it with one more segment. So from here to here, if I click my slope, I can see it's right here. It's a little hidden. It's still negative 1.6. Distance. So distance or length, again, since it's a line segment, if you guys want to do it easier, instead of clicking the points, you can literally just click the line and I'll do it for you. That's one thing I haven't told you guys yet. If you have a line segment, it makes it easier to measure distance because you can just click the line segment. 9.4. And again, if I want to do it easy, I can just click this line segment, 9.43. So all line segments are going to be 9.43. This making sense, guys? I know like some of it's like fast, some of it's slow, a lot of it's boring. How do the slopes and the line segments compare? Again, we're literally gonna say the exact same thing. In fact, you can just copy and paste it if you want. They're just being very repetitive on this. The distance between the corresponding points are the same, as well as their, let me do it a little bit better, as well as their slopes. Angle measurements, from here, um, I can record the rest, guys, but I have to go to the next class, unfortunately. But basically, it's going to be the same thing. Like, take your angles, measure it. It's the same thing as we did at the other ones. And for this, obviously, since it's translated that, what's the distance? It's going to be 7, because it's the same thing. So a lot of it is just this idea of keeping it all the same. So I'm sorry I had to rush through this one. If you guys really do want me to kind of go over the angles, um, and the line segments of the distance, make an appointment with me. But basically, you're just going to measure all the angles, and that's the same. Uh, is that fair? Like, you guys understand how to finish this up? Yes, no, maybe? All right, cool. All right, guys. And then, as always, this video will be up on YouTube by the end of